Very quickly, I'm Al from Koi. Koi is a network we built to address very large problems in the world, since it is kind of the end of the day, and I know we're in a bit of a hurry, but I want to do a quick little show of hands thing, which is usually kind of fun. So to figure out why everybody's here, it will help me to explain things in a more contextual fashion. So who is here because they really like Bitcoin? Oh, wow, actually, usually people don't come clean about that, but I'm happy for you. I also like Bitcoin, it's pretty good. Who's here because they want to make a bunch of money? Good, okay, nobody fell for that one, so that's good. In a broader sense, does anybody want to change the world? Okay, yeah, that one usually goes over better. Thank you, Peter. So I think generally speaking, the thing that's kind of interesting about this, we have this one global mission at Koi, which is to change the world, we need a better system for knowledge. Because human beings make decisions all day, and that's what mostly keeps us from dying. And we need this to be an easy and global system that includes everybody. And we also need it to be incredibly resilient. So this has led us to a set of challenges. And if you saw my talk earlier in the other room, I apologize. Some of this is slightly duplicated because we have to go to the backstory. If we want to solve this problem, we need a way of structuring unstructured data. So the global world, organic systems, very much a lot of data that is not contextualized, it's not written into human language. We also need to validate those systems, validate the inputs to them, and then build stable and mission-critical systems that run on top of this that are reliable and secure all of those against history modification. So what this generally looks like is, kind of like a blockchain, sort of. But it's actually not a blockchain, it's a much larger thing. This is that Sybil resistance bit. So the thing that's cool is Bitcoin is very much not the first thing to have accomplished this, and all the systems that have come after it are actually, well, significantly evolved from that. Koi is one of the more modern ways to do this. There's also things like Bacalhau and all kinds of other ways that people have been accomplishing this. The neat thing is this whole data thing that we talk about is actually mostly a social phenomenon and not actually a computer phenomenon. So in the Yap Islands in Indonesia, they use large rocks, or they used to use them as currency. And the way you got one of these was you got on a boat and you went across to a different island, and then you cut a big piece of rock off the wall and you put a hole in the middle of it so you could put it over a piece of wood in the middle of the boat, and then you brought one of these things back. And if you got one of these, it meant that you had to have a bunch of friends that were willing to help you go across a very large body of water on a boat and pull back a big rock. And it worked for a while, and they had a pretty functional system with this. And whoever was in charge of the boat got to keep the big rock in front of their house, and then their friends got to have social credit by being proxies of that. The tally sticks in England are another interesting example of this. So the tally sticks is this kind of interesting thing the British government came up with, where you got a piece of wood, and when you did your taxes at the end of the year, the tax collector would make markings on the wood, and then they'd split it in half. So you got to keep half of it, and the tax collector would keep the other half. And this actually worked really well for about 300 years. And then I think around the 1700s, somebody set fire to the Tower of London, and they all burned and they disappeared. So value of immutable storage, it would be great if those things could be kept in many places instead of just 2 copies. At which point, of course, the tax collector didn't have a copy anymore, and the citizens all had their own copies, and everybody forged copies. So, immutability is good. Side note on this is the art colonies that existed across the North American area, and then also in what they called statue collectives in ancient Greece. These are an interesting example of social communities building trust. And in a lot of cases, what happened here was that they would create some art that became fairly valuable because of social credit and social observance of it. And then that art would usually end up being collectively owned by the community, and they would earn fees from it, which turned out to be a pretty good way of generating revenue and building small communities. That takes us forward to the Decentralization of Government Agencies, which is a paper by the RAND Society and has this fantastic graphic that everyone in this industry is quite familiar with. The interesting thing to note here is that so far, mostly in crypto, we've been talking about the middle column, which is this decentralization thing, and what we'd really like to get to is a distributed system. But we're really not there yet, and it's taken quite a while to even get decentralized stuff even maybe working a little bit. So what I will mostly talk about for the remainder of this presentation, and then there'll be mostly, I think we have 8 minutes of actual slides, and then we can all just chat once the video camera team turns off. But mostly I'll be talking about how to get to distributed systems from here. So Bitcoin, as you all know, was a way of connecting blocks together so that you can make stuff that people can trust and that people can't abuse. This led to Vitalik going on about the ability to create this as a state transition system, which is really just a different way of looking at the same system. What this means is instead of having a blockchain that each block is independent, you use UTXOs, you use a state that's shared between the blocks, which has major benefits for being able to do things faster, and it means you can discard most of the chain after the fact, and you can just keep the latest state. And that led to lots of Lambos and made a lot of people happy. So the vision for a world computer in 2015 was never quite implemented, though. And actually, if you look at the way things have progressed, a lot of projects like LivePeer have had to do a lot of work to actually build the pieces that were supposed to be there in the first place. So we have Ethereum currently, which is a way of actually having blocks in chains that sequences data. Swarm and Whisper were two other components of this system. And what they were meant to do, Swarm was basically supposed to do what Filecoin does now and store all the data. And Whisper was supposed to validate the data going into Swarm and then lock it into Ethereum by getting lots of signatures from lots of verified identities. This never quite got built, and about 5 years ago, this post was made. Swarm, unfortunately, still hasn't figured out their incentive models, so Filecoin's a clear leader in that area, but there's also lots of other storage networks coming onto the field. In the meantime, though, no one's really figured out decentralized compute, which is what Whisper was supposed to do. It hinges mostly on reputation systems. So what we ended up getting is a whole bunch of different blockchains that can sequence data and a whole bunch of storage networks that are pretty good at holding on to it, but we don't really have anybody to do this compute part in the middle, which is, I think, why we're all here. And that's kind of the cool part. So what we have created at Koi is a thing called task nodes, which the goal of this is to provide a different kind of verifiable compute. So you have two types currently. The first one is fully deterministic machines, which allow you to have a EVM, FVM type environment where everything's deterministic and you're very limited on what you can and can't do. The second kind is fully verifiable compute in languages like Lurk and Move. Both of those systems still require you to do a lot of duplication of audit work. And so for every cycle of compute that you do, you have to do another cycle of auditing, or at least of proof generation. And that's basically like putting a stop function at the end of every line of code. So there's some major problems with doing it that way. So what we're trying to accomplish at the moment in this whole, I think, distributed compute space is we'd like to have sort of bespoke proof frameworks. So we can ask somebody to do something, and then reliably over time, we can reduce the number of times we have to duplicate the work that we're asking them to do, which we call audits, but there's lots of other ways of phrasing this. So the interesting thing that we came up with is called CARP. COD, Bacalhau. We kind of like the way that you did that one. We've called ours CARP for a decent bit of time internally, and then the other day, my co-founder told me that we actually already had an acronym for this, and I just found out. So this is fun. It's a compute, attention, and reputation protocol. You can swap out the attention part. We use attention to base reputation, but if you want to use a different way to base your reputation, you can do that as well. The benefits of using something like CARP are that you can reduce long-term audit risks by using reputation. So if you do your compute based on reputation in addition to staking, you don't have to do as many audits over time because you know that you can trust people. You can reduce the duplication of work for the same reason. You can also then generally increase your network value over time in a fairly deterministic fashion. So the more verified accounts that I have as part of my network, or your network, or any network, the less duplication we need to do, and the more compute cycles are actually useful, which is very cool. And so the other neat thing, and the reason that we chose attention, is it can reduce the amount of onboarding time required. So once we actually know that someone has a social identity that's generating some like kind of actual traction for them and that it's connected to a lot of other people, we know that they're actually not going to forsake that social identity. And they become somewhat a valuable part of this network. What we found also by interviewing a lot of our users so far is most of them won't actually behave like a rational actor and try to beat the system because they don't care. So most of them will just do what they're asked, like 99% of people. The small subset of people who really want to attack systems like this are usually better served to go and actually do bug bounties. And so what we're trying to create is a system where people want to do the right thing and are willing to do it, and where we can trust that they will do that. And if we can distribute that socially well enough, then we get to a world where people just get paid to do compute and Jeff Bezos goes out of business, which is fun. So very quickly, what is a task? A task is an executable, an audit, nodes with reputation and collateral, and this looks something like this, which is complicated. I'll walk through it really quickly because it'll be slightly easier to see. You take a task, which is a little file, some code that you wrote. You upload it onto a storage layer. We used to do a lot of stuff with Arweave. We're a little bit skeptical of what they're doing now. You register that executable file into what we call a settlement layer. So you make a little CID hash, you drop that in. And then your service nodes stake tokens to participate in this task. They also stake reputation. And along with that, they're now allowed to run this executable and submit payloads out to the network. And they can submit them to IPFS, they can submit them to the settlement layer, they can just send them to another node as well, as long as somebody checks it. And then what happens is other nodes, can be the same nodes that are doing the service, check each other's work. And they provide votes. And if during an audit period, which occurs after the work period, anybody's found to be doing anything wrong, they have a penalty. But that doesn't have to happen every time. You don't have to audit them. They do have to wait so that somebody can audit them. And this is why we invented this thing called Gradual Consensus. And then there's a payout period, and you get your stake slashed, and usual stuff. You either get a reward or you get hurt. The execution environment that we've created for this at the moment, which is super handy for most people, is a JavaScript environment. So you can push WASM into it if you want to, or you can use TypeScript. We are working on a Go and Python implementation of this as well for higher compute applications. This also comes along with full support for npm modules, which is really nice because there's 13.5 million engineers that already know how to use these things. So it's hopefully going to speed up adoption quite a bit. File system read and write, Redis cache, REST API via express.js, cron timers. You get secret injection. This is kind of neat. If you want to, when you create a task, you can ask people to go get an API key for Google Images, or for Google's character recognition API, or Google Translate, or any other API that you feel like querying, and they can put that API key right into the node. So if you want to verify Twitter tweets or go scrape Twitter, you can get all your node operators for your task to go get those keys for you, and you can use the free tier as long as you want. And you pay them in whatever token you want as well, which is fun. They also have task-specific keys for 5 major networks. So each task has its own little set of delegated keys, and you can get them to go interact with Ethereum or any other network that you'd like to use. So, one sec. Oh, we have Python and Go environments, and Ethereum, Arweave, Solana, Near, and Filecoin currently. We'd like to include a few more, so if you know of a key that we're missing, please let me know. Very quickly on the gradual consensus thing, because I know we're kind of running out of time now. The way this works, you have an epoch of work that's done first, this first epoch, and you have a second epoch during which people can look at the results that are submitted, and they can try to take away somebody's stake. You don't have to do the audits, as I said, so the audits are optional and can be chosen kind of stochastically. The neat thing about these is these epochs also layer. So when the second epoch starts, when you're verifying results, you can actually start another work epoch. So you can still get 100% uptime, and the thing can kind of run continuously. One of the cool features of this, and one of the reasons we included REST APIs in these things, is that you can also layer tasks on top of each other, which is very neat. So if you have a result from one task, like web scraping, that you then want to index through a second task, and then have search on, you can have 3 separate tasks that all read from each other's nodes. And now you've got a fairly stable system where you don't think anyone's going to misbehave that can provide normal application layer services. We have people working on search now. We have some people working on indexing. We've got people working on bridging blockchains, web scraping. Some people are hosting REST APIs for social media type apps, doing indexing of NFTs. We've got an image processing tool that makes thumbnails in different sizes for different images that you have. And it all depends on finding the right audit for these different systems. So if anybody has questions afterwards, I can go very in detail about what kind of audits we have. The cookbook, very quickly, is these things called proofs. So you're all familiar with proofs. We have them for random numbers now, so you can use VRFs. Those are pretty efficient. If you layer lots of VRFs together, you can get pretty decent randomness from a large group of nodes. Attention tracking is another thing we invented called proofs of real traffic. So that basically connects a whole bunch of our nodes together to verify that someone looked at content, which is how we distribute our tokens. And you can do deterministic actions like transformations, indexing. You can do time-based things, which is super fun. We forked Solana, so we have timestamps for everything that happens in the network. And so you can just pull a timestamp in, and then you can use that to verify that something happened at a specific time. You get a wallet signature from one side of a transaction, and then you get it from the other side. So if you want to query a REST API, you sign something, you send that to request the file. The person who actually sends you the file back also signs something. Now you've got 2 parts of a proof that get both of you paid. And so you can get paid for querying a REST API, which is pretty cool. There's combos like search, and some of this. There's some shortcuts as well. So use APIs and direct communications. Use storage layers, not blockchains for the most part. So you can write a CID into a blockchain, and that basically does everything that you would need to do to make a smart contract work most of the time. If you've got a ton of signed payloads that go into IPFS, you can write that CID full of signed payloads into a smart contract, have everybody verify it, and then all the nodes that verify it just submit a Boolean on-chain. So it makes it way, way more efficient. You can also use witnesses and audits instead of consensus. So each of these task groups is potentially thousands of nodes. So you don't need a general consensus network for this. You need a consensus network like Ethereum mostly to sequence transactions. So you don't really need this kind of general smart contract language that everybody's been trying to build. And then finally, your speed of results and speed of verification are independent. So if I know that a certain group of nodes are consistently reliable, I don't need to wait till the end of the audit period to use the data they're creating, which is very helpful. So you can have basically 100% uptime. And the system might go offline sometimes, but so does Google search. So things sometimes go down. Very quick flywheel point. Last year, we got 30 million views on the network, which minted 300,000 tokens to about 45,000 users who all now want to run nodes on their computer. So we're in the process of giving them the ability to take that credit that they're going to be building up by running tasks on their device reliably, and then giving them the ability to then deploy a node onto actual hosting and get a GPU instance, or something that can actually really do some serious number crunching, or even a Bacalhau instance. The real hinge of all this stuff is attention. It's how we get the original credit to give people a chance. The neat thing about this, though, is that the reputation that they're building up on Koi can also be useful to all of you. So if you're building something and you need really trustworthy people, we're trying to build a gigantic group of them. And our goal is mostly to get them paid. We don't even really want them to use the Koi token. So yeah, some stuff there. Thank you for your attention.
And follow-up question for you. One of the things that we run into in a lot of these decentralized networks is getting routing user traffic, the life of a web request, to these decentralized networks. Is there a pattern in Koi network, or a pattern that we should think about for other compute networks, where if I need to go request something from myapi.com and that needs to go through some sort of a load balancer maybe, how do you guys think about that problem? Are there any lessons learned about sort of feeding that out to these decentralized ecosystems?
I think the really quick answer is reputation. It's sort of kind of what Jan was saying before. So tracking the reputation of each node at utilitarian tasks. So if I need to route traffic in a certain area of the world and somebody makes a request from that part of the world, I know which nodes in that area are going to be reliable. Our goal is mostly to create with tasks a open environment where people can test these kinds of incentive models. But we are working on a proxy network that will hopefully accomplish this. So that's sort of the general idea, though, is if you have enough reputation from these people, then you know that this one node that's running in an AWS data center is going to consistently route traffic for you, and now it can be part of that backbone. General scope of things. It's not easy, though.
Very good. All right. Thank you so much, Al. Cheers.
Thanks, folks.
All right.